Hello and welcome to our very important discussion. And the topic that we will discuss today, our objective for today is histone organization. Histone organization. Histone organization. And histones are organized with the DNA in a complex known as the nucleosome. And just a little caveat that uh, what you need to know is that some professors and teachers may make a lecture or a lesson under the title. The title of the topic would be DNA organization. DNA organization. And that is not very precise. There is DNA structure and function. And then there is histone organization, because we are looking at the organization of the histones around the DNA and the formation of the nucleosome. So it's the histone organization. You have these octamers, these subunits of histone coming together, and DNA being coiled around them, as we will see in a little bit. And that is the organization of the DNA. But so that's the organization of the histone. But when it comes to the DNA, we talk about the structure of the DNA, the double helix and the major groove and the minor groove, and the purines and the pyrimidines, and the hydrogen bonding between them, and the base pairing, the G's with the C's and the A's with the T's, and so on. So that's the structure of the DNA. And the function of the DNA is how it is a template for making these, nascent transcripts that will later be modified and then translated in the ribosome to give us our proteins of interest. So the function of the DNA is that it's the site that it provides the template for transcription, and it also provides a template for its own replication. But when it comes to organization, it's actually the histone organization. We need to know that the DNA must be in the form of the nucleosomes. Otherwise, each cell has about 30, each chromosome, there are about 30 million nucleosomes. 30 million nucleosomes in the DNA. And so if you remove these nucleosomes and you spread out the DNA as one really long line, you would see that it is a magnificently, and that is one cell. That's the DNA in one cell. So imagine all of this DNA in the body is just put in the form of continuous strands that will be in the length of light years. So the nucleosome structure is very important because it provides for us, for the DNA, structural integrity. So let's look at what the nucleosome is comprised of. The nucleosome is an octamer. It has 8 subunits, but it is in the form of a double. So we have 2 subunits of each. We have the histone 4 subunit, and there's 2 of that. And there's the H2A, histone 2A subunit, and there's 2 of them. And there is the H2B subunit, there's also 2 of that. And there's the H3 subunit, and there's 2 of them. So we have H2A, H2B, H3A, and H2A, H2B, H3, and H4, and there is double of each. Okay. It is in the form of an octamer. That's an 8. So a monomer is 1, a dimer is 2, a trimer is 3, a tetramer is 4, a pentamer is 5, a hexamer is 6, a heptamer is 7, an octamer is 8, and a nonamer is 9, and a decamer probably is a 10. So we have an octamer that is made by the duplication of 4 subunits: H2A, H2B, H3, and H4. Okay, and what happens is, in this octamer complex, the DNA would come and wrap around almost twice. This is very important to know. The DNA strand would come and it would not wrap once and go out. It would wrap once and 0.8. So 1 and 80% of the second turn. So we have almost 2 turns minus 20% of that second turn. So we have a turn and 80% of a second turn, and then it would go out. So each nucleosome has the DNA wrapped around itself not once but almost twice. So this is we have almost 2 coils, not 1. So if I have a thread, do I have a thread? I do not have a thread. Let's see what I have here. Let's assume that we have this thread. So, and the octamer we said is a double. So what we will see is it will come, like this is the double, I'm sorry, this is the double, this is the 4 here and 4 here. It would wrap once and then almost twice, and then it would leave. It would leave to another nucleosome. So now we have almost two turns or 2 coils around the nucleosome. Okay, if we remove the part that has been coiled around the nucleosome and we count how many base pairs, how many will we find? 148. That is very important to understand. To see the range, some books will say 146, others 147, but others will say 148, but it's in that range. We will have almost 2 rounds of coils around one nucleosome. We will have 2, and these 2 are actually 147 base pairs. And then the DNA would move out to an intermediate histone subunit known as the H1 subunit, or the linker DNA. The linker DNA is the part of the DNA that is not in a nucleosome. So we have our DNA wrapped around the nucleosome once. Like let's say this is the nucleosome. That's the first. These are the 4 subunits, and these are our other 4 subunits. The DNA would come and wrap once, and then wrap 0.8 of a second turn, and then it would go out into another nucleosome where it would wrap once and 8%, and there would be a part between the 2 nucleosomes that is not wrapped around any nucleosome. This is the linker DNA, and it has a histone subunit that comes with it, known as the H1 subunit. So at this point, you will be asked, what is the histone subunit that accompanies the linear or the linker DNA? What is the histone subunit that accompanies the linker DNA? And that is H1, the H1 subunit. You will be asked, the histone complex is comprised of how many subunits? 8. Don't say 4 doubled, no, 8, because we have the H2, 2 of that, H2B, H2A, 2 of that, H2B, 2 of them, H4, 2 of them, and H3, 2 of them. If you are asked to name, you could be asked to name the subunits of the nucleosome. You should say H2A, H2B, and H3 and H4. How many turns are taken by the DNA around the nucleosome? 1.8. A whole turn and almost another whole turn minus 0.20 or minus 0.2. That is 1 and 80%. That is 100% and 80%, and then it will move on to become a linker DNA and then go on to be turned around another nucleosome, about 2 turns, except 20%. So a turn and a little bit a little less than 2 turns. If you count how many subunits are wrapped around that DNA that is coiled around the around the histone complex in the nucleosome, they are about 148, 147, or 146, but it's usually 148 subunits. Okay, the second thing we want to talk about, we have in our nucleus, we have the DNA, and we have the same DNA in all of our nuclei in the body. In all of our tissues, all of our cells have the same DNA. Well, then why is it the case that we have a nerve cell enabled of performing what the nerve cell or the neuron does structurally and functionally? We have a hepatocyte, we have a cardiac myocyte, we have these different, we have these nephrons, we have these different types of cells, although the DNA is the same. Why is it that we have different cells, morphologically different, structurally different, and functionally different, although the DNA is the nucleus, in the nucleus is the same? And the answer is because although all the DNA is in there, but it is not all transcribed. So the DNA in the neuron that makes the neuron what it is and provides for the neuron through transcription all the proteins that the neuron needs and all the growth factors that the neuron needs to proliferate and grow and become what a neuron is transcriptionally active only in the neuron. In the hepatocyte, what makes a hepatocyte looks like a liver cell or a hepatocyte and performs the actions through these proteins that are unique to the hepatocytes. It's because in the DNA, the region that is expressed and transcriptionally active is the region that makes a hepatocyte what it is. So just because we have DNA does not mean it is all transcribed. Only a certain part of it that is transcribed depending on which cell are we looking at. So that when they looked in the microscope, the light microscope, they saw that in the nucleus there is light regions and there are dense dark regions. And these dense dark regions are the inactive. This is very important. The histochemically dense and dark regions of the chromatin, they are known as the heterochromatin, and they are inactive. So inactive DNA is a heterochromatin, transcriptionally inactive and histochemically dense and dark, while the euchromatin, euchromatin is transcriptionally active and histochemically light. So what makes a neuron is that the euchromatin that is transcriptionally active, that is being regulated, and the region that is light and not dense, that is the region that makes a neuron a neuron. And the heterochromatin is the part of the DNA that makes other cells what they are. So each cell makes and encodes and uses the part that it needs, and the part that is active will be light in the microscope and will not be dense, will be dispersed. So that calls for the idea that this nucleosome structure must be modified. You cannot have the DNA tightly coiled. There must be regulatory mechanisms that loosen up the DNA. Let's say the cell needs to transcribe a part of the DNA that is wrapped around the nucleosome. What are we gonna do? We're gonna say it's wrapped around the nucleosome, it cannot be transcribed? No, there are regulatory mechanisms that would loosen up the DNA and make it accessible to all these regulatory proteins, and for genetic expression and for transcription factors to come in and transcribe for us the proteins we need. So you need to know that there are regulatory mechanisms, and we will talk about these regulatory mechanisms. So what you see here, you see the DNA, for example, in the form of a heterochromatin, where it is so close and tightly packed and dense and dark, histochemically dense and dark in the light microscope, and compacted and transcriptionally inactive. But when we need that part of the DNA to be transcribed, we perform regulatory mechanisms, or the cell performs regulatory mechanisms that converts the heterochromatin to euchromatin. Okay, and the euchromatin is active, is transcriptionally active, and histochemically dispersed and spread out and light. So when we compare the euchromatin, the heterochromatin, the euchromatin is light while the heterochromatin is dark. The euchromatin is spread out and dispersed while the heterochromatin is dense, and transcriptionally the euchromatin is active while the heterochromatin is inactive. What are the regulatory mechanisms that convert heterochromatin to euchromatin, and after transcription is done, we go right back to heterochromatin? Okay, the first process is the acetylation. So acetylation, you have to know that the DNA is negatively charged due to that phosphate group in the phosphodiester bond. So the DNA is negatively charged. So the histone must be positively charged in order for the two charges to attract, and we have a compact, tight structure. So if we want to loosen up, what can we do? Can we change the DNA charge? We cannot, but we can change the histone charge. And what happens is we perform acetylation. And when we perform acetylation, what happens is the positive charge on the lysine residue in the histone will become neutral. So now there is no positive charge. You have a negative charge and a neutral charge. So that would release this tight coil. So the first regulatory mechanism is acetylation, where we neutralize the positive charge of the lysine residue in the histone, and then the tight bond between the negatively charged DNA and the formerly positively charged before the acetylation would be released, and now we would have a dispersed or a spread out DNA that is accessible for transcription. Now, another procedure is the demethylation. So obviously methylation would make the DNA very tight and compacted. So methylation would be tight and compacted. Acetylation would release. So methylation has the same effect as deacetylation. And the third regulatory mechanism is phosphorylation. When we phosphorylate the serine residue when we phosphorylate the serine residue in the histone, what happens is we have euchromatin. So acetylation, phosphorylation, so acetylation of the lysine residue, demethylation of the arginine residue, and phosphorylation of the serine residues, they have the same effect, and that is they will convert heterochromatin into euchromatin, and it will become transcriptionally active. While the opposite, methylation would cause a tight compacted heterochromatin, and deacetylation, which is the removal of the acetyl group, and now the lysine residue will be able to regain its positive charge, and the dephosphorylation of the serine residue will have the effect of remaking the DNA tight again. You need to know that. You need to know that acetylation loosens up the DNA, and the deacetylation brings back the DNA and makes it tight again. How? We have acyl transferases, enzymes known as acyl transferases, they perform acetyl transferases. These acetyl transferases add an acetyl group to the lysine residue in the histone and convert it from a positive amino acid into a neutral amino acid. And now the negative DNA can no longer bind to the positively charged amino acid in the histone, the arginine or the lysine residue, and now you would have a released or a spread out DNA. Methylation. Let's now. I'm sorry. That was acetylation. Deacetylation. You have histone deacetylase enzymes. They remove the acetyl group, and now the lysine would regain its positive charge, and you would have the DNA so tightly compacted again. Now let's move to methylation. Adding methyl groups will have the effect of making the DNA so tight and condensed. Demethylation would release that tight DNA compaction. And then we have phosphorylation. We're phosphorylating a serine group, a serine residue in the histone complex would cause the spread out of the coil, while the dephosphorylation would cause it to come back, become tight again. So you need to make sure you review that. So yeah, in cancer treatment, there are drug therapeutic pharmaceutical interventions that target this process, and they are trying to have drugs that prevent cancer cells from using acetylation. Those acetyl transferases inhibit them so that the cancer cell can no longer spread out the DNA and transcribe the proteins it needs to make growth factors and to grow and proliferate and become metastatic. They also target the demethylation enzymes that also are important for the loosening and of the DNA and making it active. And also they target the enzymes that phosphorylate the serine residues in the histone complex and make the DNA of the cancer cell accessible for transcription. So these here are very important for cancer treatment. Okay, so make sure you revisit this topic again. If you have any questions, I'll leave them down there. Thank you very much. I'll make sure to show you the diagrams one more time. Okay, so we have the histone octamer here, the almost 2 coils, 1.8 coil. You have the H2A, H2B, H3, and H4. And then you have the heterochromatin that is tight and condensed. You have the H1 histone subunit with the linker DNA, and you have acetylation, demethylation, phosphorylation, leading to the spread out of the DNA, making it active and transcriptionally accessible, while methylation and deacetylation and dephosphorylation cause for us a dense heterochromatin. Thank you very much. See you in the next video.